So we're happy to have Wayne Hayes today. He's a professor at UCI, Irvine. Wayne is a CS professor, but he is a former U of T grad student and wrote a bunch of papers with Scott Tremaine. So he is connected to CITA. And he's going to tell us about automated image classification.
Sure. All right, thanks. There's not going to be all that much theory in this talk, but I'm going to tie to the end at how, how observations, these particular observations might be able to be tied to theory. So the program is called SpArcFiRe, the algorithm developed by my graduate student Darren Davis. I think it's kind of indicative of how desperate astronomers were for data on the structure of spiral galaxies that they invented the Galaxies project, right? How many of you have heard of the Galaxies project? A couple of you, right? So it's like basically 12-year-olds classifying galaxies over the web, about 250,000 of them. Any volunteer with 5 minutes of training gets to classify a galaxy over the web. And so it provided, and still is providing, lots of observational qualitative, I would call it qualitative data, but quantitative data has been few and far between. So it's called SpArcFiRe. It stands for Spiral Arc Finder and Reporter. That was Darren's name. And it's actually, we have a preliminary web interface available for it too. So if you're interested, you can go and find your favorite picture of a spiral galaxy and have SpArcFiRe analyze it for you. So the first thing I'm going to say is that Hubble's classification system has been around for millennia, and but the problem is it's a discrete classification. Galaxy morphology is not discrete; it's continuous, right? There's a continuous. Basically, all the variables that there might be are all continuous. It's also somewhat subjective, right? Even if you take professional astronomers and have them show them a picture of a galaxy and say, is this an SAB or an SBC or an S whatever? You'll get a distribution of answers, even from trained professionals. We would, prefer to have something that's objective and quantitative to be able to compare quantitatively to theory. I think it was Lord Kelvin a few centuries ago who said something along the lines of, "It's not science until you can quantify it." And this isn't really quantified yet. So first of all, let me very briefly describe to you how our algorithm works. Given any image in which the galaxy you want to analyze is approximately centered, it will use an iterative Gaussian, two-dimensional Gaussian to actually find the disk of the galaxy automatically. And this is a very standard computer vision technique. And then given this image that we've found and centered, the magic sauce is a thing called an orientation field. So astronomers have been trying to kind of do something like this for decades. I mean, even when I was a graduate student, I wanted to do something like this, but I don't think the techniques were there. And the obvious thing to try is to try to write some clustering algorithm that clusters pixels according to brightness, and it simply doesn't work. It just doesn't. But there was a guy named Kinman Au at Pittsburgh, I think, who had an aha moment in 2006, and his thesis was all about creating what are called orientation filters. So basically, an orientation filter is, imagine putting jail bars down on this image, a bunch of black and white bars, and you look between the bars and find regions where there's a bunch of pixels that are all oriented vertically. Then you change the orientation of the jail bars, and that gives you orientation. That gives you regions of the image that have particular orientations, and then you can assign an orientation to each pixel. So this can all be made mathematical, but I'm just hand waving to make it easy to understand. And once you have assigned, so basically for here example, this means all these pixels are all together. They respond strongly to a vertical orientation field. Once you have an orientation is like a vector but with no arrow. So this orientation is exactly the same as that orientation because there's no arrow at the end of the vector. Once you have each pixel assigned an orientation, then you cluster pixels based on orientation using any standard machine learning or clustering algorithm. And then here's what you get. The magic is pretty much done. The cyan pixels all clustered together based upon orientation. The green ones all clustered together based on orientation. And of course, like in any astronomical observation, there's some noise arcs as well. Once we have these clusters of pixels, we use a least squares algorithm to fit a logarithmic spiral arc. So a logarithmic spiral arc is just a mathematical curve that has the property, if this is the center of your galaxy and you draw concentric circles around the center of the galaxy, a logarithmic spiral arc always has the same angle, subtends the same angle for all circles. And it's been known for, I don't know, decades that a logarithmic spiral arc is a relatively good description of the curve in in the arms of spiral galaxies. And what really is amazing, it actually turns out to be a fantastic approximation. I mean, here we have a curve that goes around almost 2 pi, and that particular curve follows the arm very, very well. And that's typical of most spiral galaxies we see. And as far as I know, I was just at, who's heard of the DDA, the dynamical, you've all heard of the AAS, right? The American Astronomical Society. One of the divisions is called the Division for Dynamical Astronomy. The reason I'm here is because they had their conference last week in Philadelphia, which is nearby. And Jerry Selwood is probably one of the world's leading experts on spiral arms. And he says, we still don't understand why a logarithmic spiral arc is a good description of a spiral arm. Anyway, so any questions on the algorithm? So once you have this, you can do cool things like, well, here's the list of pixels that all belong to this arm. So you can start doing whatever measurements you want on this particular arm. On an arm-by-arm basis, you can get brightness profiles, Searsic profiles, whatever you want, or measurements, or absolute, total luminosity coming out of that particular arm, or whatever. You also get a list of these least squares fits, these arcs for each galaxy. So you can look for galaxies that have. We've run this algorithm on the entire Sloan database, so I'll show you later how you can do a query of our ARC database. Find me all galaxies that have arms longer than blah, or find me, all galaxies that have more than 3 arms, or whatever. So it's all quantitative and objective here. Here's just some typical examples of nice galaxies. Although I didn't talk about it, we can also find bars in barred galaxies. So here's just 6 examples of reasonably nice-looking galaxies. Here's one where this is one of the examples of the longest arms. This arm actually goes around more than 2 pi. Actually, both of them do. Both of them go around more than 2 pi. So there are some really long arms out there, and the logarithmic spiral arc is an amazing description of how, with a few small exceptions like here where this arm kind of straightens out a bit, but for the most part, it's a good description.
How well defined is it? What an arm actually is. For something in last side.
I'm gonna. Yeah. I'll give you your $10 later. Perfect question. Like, I don't know if it's the next slide, but very soon I have a slide titled "What is an arm?" Before I get there, though, let's. So we have pitch angles for now 100,000 galaxies. We actually restrict most of our analysis. So when comparing with other data sets, we compare with Galaxy Zoo, and there's a particular set of about 30,000 galaxies that the leader of the galaxy, the PI of the Galaxy Zoo team, sent to us, saying these are all the high quality, really confident, where the humans were very confident and agreed with each other. So this is just 6 samples from that. So you might ask, how reliable are the pitch angles that we measure? So although we have pitch angles for, depending on how you count, either somewhere between 30,000 and 100,000 galaxies, pitch angle measurements for arms have only been done on a few dozen galaxies, and they've all been pretty much done by hand. Ma in 2001 did a sample of, I think it was 60 galaxies, literally by hand. He just used his mouse to click on arms and trace them out, and then did a least squares fit to his mouse clicks. Ben Davis and Mark Sager, both at the University of Arkansas, had a Fourier-based method which required a lot of human intervention, although it was slightly more objective. But you can see at the very least that they're definitely, so this is the pitch angle that we measured and the pitch angle measured by Ma, and it's plus or minus depending on which way the arms wind. Oh, by the way, in these images, red arms wind this way and cyan arms wind the other way. The Galaxy Zoo coined the term S-wise and Z-wise, so this would be an S-wise curve, because clockwise versus counterclockwise is ambiguous, because some people think you're counting from the inside and some people think you're counting from the outside. So S-wise and Z-wise, as the Americans say, I think is a more objective term. Anyway, so you can see that for the most part, there's a lot of scatter, but we definitely agree on at least the winding direction in all cases except one where it was close to 0 and the error bars at least span. But there's quite a lot of scatter. So the question is, should we be worried about the scatter? Because I just finished telling you that the logarithmic spiral arc is a really good measure, is a really good description of a spiral arm. So why is there so much scatter? Anyone have any hypotheses?
Oh, I mean, but the outlier should just check it by hand and see who's wrong.
Yeah, so we actually went to visit Arkansas and compared our Fourier method to theirs. And yeah, in the case of the really bad outliers, it was just, there was weirdness in the galaxy. I mean, some galaxies are complicated, as you'll see in a second. So it turns out that you don't really need to worry about the scatter, because one of the things we discovered here that I don't think was really all that well known before was that although each individual arm is well described by a logarithmic spiral arc, it turns out that different arms can have different pitch angles. So what we do here is to try and figure out why there was so much scatter in the previous figure, Darren had a realization that perhaps the scatter in the previous diagram has nothing to do with different measurements from different algorithms, but it actually has to do with the fact that different arms in the same galaxy have different pitch angles. So these three curves here, one of them, I forget which one, let's read it. Cumulative distribution of pitch angle discrepancies between two arcs in the same galaxy, right? So the red curve is the discrepancies between two arcs in the same galaxy. And the blue and the green curves are measurement differences between our algorithm and the other two algorithms. And since all the curves, and the other guys only measured one pitch angle per galaxy, right? So with us, we can measure the difference between arms in a single galaxy, and we can also measure our average pitch angle versus the other guys. And since all the curves are very, very similar, we hypothesize that the scatter in this diagram is actually due to the fact that different arms have different pitch angles. It's not an algorithmic difference. It's due to the scatter in the actual pitch angles of real galaxies. Questions? And I will have a bit more detail about that in a second, but let's continue on with comparing ourselves to other measures. So this is a very busy table. Basically, it boils down to we're comparing our winding direction. So asking a very simple binary question: which direction do the arms wind? Do they wind S-wise or Z-wise? Just a binary question. How well do we agree with humans across a sample of 30,000 galaxies? So first of all, we have to ask, if for each galaxy, how much do the humans agree? So about 50 humans saw each galaxy in the Galaxy Zoo survey. The top row asks what was the percentage of humans that agreed with the majority vote. So in this case here, at least 80% of the humans agreed with the majority vote. Here, 95%, and this is the case where everybody agreed with a particular winding direction. Let's skip down to the third row for a second. The inclusion rate is what percentage of the 30,000 galaxies we're looking at were included in this set. So in other words, this is saying that there were 20% of galaxies almost, actually 20.6% of the galaxies didn't have at least 80% agreement. When you ask for 100% agreement, only 12.5% of the galaxies had 100% agreement between humans. Okay, so we call that the discernibility. How discernible was the winding direction to a human? The second row is a measure of confidence with our algorithm. We ask, take the two longest arms that our algorithm found, and do those two longest arms agree in winding direction, right? There are some galaxies where the longest arm is red and the second longest arm is green or cyan, right? In that case, the answer would be false. Our two longest arms don't agree, so we're a little bit less confident in our classification. Over here, we demand that we have the two longest arcs in our output do agree with each other in the winding chirality. So this column is the column I'm going to focus on. This is the column where 100% of the humans agreed with each other on the winding direction, and our two longest arcs agreed with each other. So we're fairly confident that we're right. Now, there are only 10.9% of the 30,000 galaxies that satisfied this. So there's about 3,300 galaxies in this set now. Okay? Of those 3,300 galaxies, the mean discernibility, so remember the number up here is minimum discernibility. In a case of 100%, the mean discernibility is 100%. All the humans agreed. So now let's look at various ways for us to calculate the winding direction. One is just to take the majority vote across all arcs, regardless of length. That only agrees with the humans about 88% of the time. Another way is to say, let's throw out all information except the chirality. Chirality is the technical term for winding direction. Throw out everything except the chirality of the longest arc. It turns out that the longest arc alone, as long as the top two agrees 99.6% of the time with the humans. The kind of the most sensible measure that we use is an arc length weighted vote. So we take each arc in our output and weigh the votes by the length of the arc, so the longest arcs have more weight. And in that case, we get 99.5% agreement with the humans. So when the humans agree 100% and we're pretty confident and we use a length weighted vote, only 0.5% of the time do we get it wrong. And this is just winding direction. So any questions? And the reason that we recommend the length weighted vote is because it does substantially better in the cases that our longest arcs don't agree. So this works across a larger set, and we still get at least 95% agreement. The interesting thing here, actually this is a really cool thing here, the mean discernibility. Remember, discernibility is what fraction of humans agree with the majority vote. The mean discernibility in this case here, where at least 80% of the humans agreed, is 92.2%. Turns out that we actually do better than the average human, because this number also corresponds to the average human's reliability. How often did the average human agree with the majority vote? We actually do better than the average human in discerning winding direction, at least in the cases where humans are less than 100% certain, because this number here, 96, is greater than 92. And there's a proof of that, like a mathematical proof of that statement in the paper we've submitted to AppJ. Any questions? I see lots of furrowed eyebrows. So we're still kind of verifying. Oh, right. So now, down here, in this number here, we're in 99.5% agreement with the humans. There's about 3,000 galaxies in the set. That means there's 15 galaxies, only 15 galaxies here, in which we disagreed with the humans. It's kind of instructive to go look at those 15 galaxies and see what the hell went wrong. If it was so obvious to the humans and our two longest arcs agreed with each other, how could we have gotten it wrong? So of those 15 cases, they basically fall into 3 categories. These are what I call the pathological cases of disagreement when the humans were unanimous, and there's only 15 out of about 3,000 cases. One case is where the arms were so dim that the ellipse fit, the very first step of our algorithm that tries to find the disk of the galaxy, missed these dim arms and zoomed into this part here, right? So there were, I think, 3 cases out of 15 in which we zoomed in which our automatic algorithm trying to find the disk zoomed in too far past really, really dim arms. Right? To a human, you look at that and it's like you can obviously see which direction it is. You can see how the humans were 100% agreement. Our algorithm just zoomed in a bit too far past the dim arms, and then all the arcs were basically garbage. Another case here where the humans would agree very obviously is occasionally our algorithm just finds, we're clustering pixels according to orientation. This particular galaxy here, it's kind of flocculent. The arms are kind of short and there's kind of patchy stuff all over the place. Our algorithm can occasionally be confused and basically found an arc along here, right? And you can see how an algorithm, which is looking around locally basically, could be confused and think there's an arc there. So that is this big long red arm. And there was another garbage arc found in the center where there's almost a ring here, kind of, right? So basically these 2 red arcs are both spurious. There's something that the human eye wouldn't easily see. And they also happen to be the 2 longest arcs, and they're wrong. And furthermore, the sum total length of these 2 arcs is longer than all the blue arcs that are correct. So the length weighted vote goes to these 2 guys And it's just wrong. And I think there were 6 cases of that out of 15. Either 6 or 8, I forget. In this case here, the 2 longest arcs are correct, and there's a bunch of red arcs that are incorrect, but the sum total length of the incorrect ones is a bit longer than the 2 correct ones. Right? So those are the 3 kinds of errors that we found. Now, this is only 15 cases out of 3,000. So one of the statements we make in our paper is that you might be tempted to try and fiddle with the algorithm a little bit to fix these errors, but there's only 15 cases out of 3,000 galaxies, and Darren has spent the last 4.5 years fiddling with the algorithm to get to the point where we're in 99.5% agreement with humans. And any changes you make to fix these will likely introduce errors in other ways, because galaxies are really, really complicated, and there's so many different types of galaxies. This is probably these are pathological cases. Any questions? Now let's talk about winding tightness on the Galaxy Zoo website. So the way the Galaxy Zoo website worked is that humans were presented with a picture of a real galaxy and then with some cartoon galaxies. And they were asked to click a button. Which one of these cartoons most resembles the real galaxy? And when it came to arm tightness, they were presented with these 3 icons: tight, medium, and loose. Which of these cartoons most resembles the real image? Our algorithm outputs an actual pitch angle. Now, remember that different arms have different pitch angles. We output the length-weighted average pitch angle. So we get a number for the pitch angle in degrees. So a low pitch angle corresponds to a tight wind, right? Low pitch angle means this angle is low, which is a tight spiral. So when we measure a low pitch angle, and the blue curve here is the fraction of humans who voted for tight. And you can see that when our pitch angle is low, the fraction of humans that voted for tight is quite high. And as our measured pitch angle increases, the fraction of humans who voted for tight decreases down to almost 0. Red is the fraction of humans who voted for loose. And when we measure a low pitch angle, very few humans vote for loose, and the number of humans voting for loose increases. Turns out that hardly anybody ever votes for medium. Turns out we kind of discern from the data that people would tend to choose medium if they weren't quite sure. The difference between the dotted lines and the solid lines is I lied a little bit. The dotted lines are over all galaxies. So there's still, the majority voted for loose here. The solid lines are in the top quartile of human agreement. So when the solid lines are across galaxies where it was if you sort galaxies by how certain the humans were, the top quartile. So when the humans were certain, there's a very high correlation with our measured pitch angle. And when the humans were and across all galaxies, there's still a correlation, right? Red goes down and blue goes up, other way around. Questions? Pardon me?
The points at the end of the graph.
Oh, why is there garbage here?
Well, no, why does it suddenly take down the record?
The number of samples here gets really, really small. Actually, we changed this figure for the paper because we made the bins bigger. There's basically only 1 or 2 samples in here. Yeah, it's just small sample size, yeah. One of the other icons or cartoons that the humans were asked to compare against is number of arms. How many arms do you see? 1, 2, 3, 4, more than 4, or you're not sure. Right, so these are the cartoons the humans were presented with. Turns out that humans find it very difficult to count arms, or at least to agree with each other. The blue curve here represents we really should make this a probability so it's consistent, but this is over 30,000 galaxies. So over the 30,000 galaxy sample, look at, so there's more than 2 choices here, so it's very rare that there's a majority agreement. There's simply a maximum vote, because there's 6 choices. So the votes are spread evenly across, not evenly, they're spread quite evenly across 6 different choices. But if you look at the maximum vote and ask, what is the fraction, if you just look at the maximum vote across all these 6 choices for each galaxy, and plot the maximum vote proportion. So this number here, for example, says out of 30,000 galaxies, how many had a maximum vote that was like 0.55? So only from here up was there a majority vote. Down here, the maximum vote was less than 50% of the humans. But what you can see here is that there's a lot of scatter here. The green represents the highest quantile. So where the arms were really obvious and the humans agreed, there were even quite a few cases where the humans agreed 100%. But for the most part, humans don't agree on how many arms there are. However, what we can do is try to figure out what a human refers to as an arm quantitatively. So what we did is we look at our own, so what we do is we look at we get a galaxy, we look at the arcs in the galaxy, and we say how many arcs are longer than some certain number of disk radii. We use disk radii as the length measure, so radians basically. We ask how many arms are longer than some certain length. And it turns out that, 75 pixels. We in the first step of our image, we scale all images so that a disk radius is 100 pixels. So when this says pixels, it means 0.75 radians long, basically. Turns out that if you ask the question, how many arcs do we see that are at least 75 pixels long, that number corresponds quite closely to the maximum vote proportion for a given galaxy. So it turns out that, if there were 3 arcs, each of them longer than 75 pixels, then the maximum vote was most likely 3 arms for the humans. So now we can actually tell you, we can go in reverse. We can tell you, what does a human consider an arm? Well, an arm has to be at least 0.75 radians long before they'll call it an arm. This really busy figure here just basically says, so the red is the proportion of people for this galaxy that voted for 1 arm when we measured 1 arm at least 75 pixels long. Green is when the humans voted for 2 arms and we measured 2 arms. Blue is when the humans voted for 3 arms and we measured 4, right? So we can see here now that 1, 2, 3, 4, more than 4. Now we get a fairly good agreement with the human arm count, with the human maximum vote arm count. Any questions? The takeaway message here is that we basically, once we set an arc length to call an arm, then we agree with the maximum human vote for arm count. So, who was it that asked what's an arm? There we go. You get your $10 later. Turns out that defining an arm objectively is hard. This is a picture of an M101, very close, nearby galaxy. And this is output just from 3 versions of the code. All right, I think this is from about 3 years ago. This is about 2 years ago, and this is actually the current output. Remember, it was whatever 210, whatever. So this is not. We didn't actually do any formal experiments. We just went back and found the version of the code a couple years ago that parsed M101, and then a year ago, and then now, and you can see that there's some discrepancies here. One of the things that a human might look at is there's kind of this big wide arm here. Sorry, this is the interesting part here. There's an arm right here that kind of forks, right? It comes out, and then right here it splits in 2. You see that? Our code doesn't look for forks. It just looks for arcs. And in this version of the code 2 years ago, we kind of see the fork, although we don't really call it a fork. We have this arm segment here. We have a different arm segment here. And this green cluster here represents another arc that's along here. Then about a year later, after having changed the parameters in the algorithm a little bit, we see something different. Now we see that what was the green and cyan arcs have been merged into 1 arc. And it's not a great fit. The curve actually goes outside of the arc here a little bit. But it's still not too terrible. And so we actually wonder whether, if there's any physical reason that the logarithmic spiral arc is a good description for arms, we actually hypothesize that this is actually a physical arm of M101. And this thing that we see as a fork with the eye is just kind of a random alignment of gas clouds or something. Maybe. It's just a hypothesis. Who knows? In any case, both of these versions of the code were a little bit less stringent in the least squares fit. That's why this is a pretty bad fit here. Now, in the most recent version of the code, we do two things. First of all, we fill in all the holes. So using a morphological operator. And second of all, we demand that the least squares fit be quite a bit more stringent. So now we actually we still don't see forks, but the part that the human calls a fork, we actually model as a separate piece. And then the rest of it are all modeled very nicely by logarithmic spiral arcs. So M101 is a bit of a mess. The point of this is that it's difficult to objectively define what an arm is. So we don't actually refer to arms in our paper. We just refer to spiral arcs. Each one of these is just an arc. And we leave, what's an arm to you guys. Any questions? That's one of the problems that you get when you start to quantify things. You start to find, difficult things to define. So I claimed earlier that individual arms in different galaxies can have different pitch angles. Here's a really nasty example. This is NGC 5054. These things here are masks of bright foreground objects like stars and stuff. But this galaxy is a bit of a mess. But in any case, there are 3 long arcs here, neglecting this one. And they have vastly different pitch angles. This one's 21 degrees, this one's 24 degrees, this one's almost 39 degrees. Right? There's quite a big difference here. Now you might say, well, this is obviously some kind of perturbed galaxy. It's a bit of a mess, so it's not really fair. But what you can do is you can ask, let's take the 2 longest arcs. And in this case here, it would be this one and this one. This one's 24.4 degrees. This is a 14 degree, roughly, 14.5 degree difference between the pitch angles of the 2 longest arcs. You can go across our entire sample of 30,000 high-resolution galaxies and ask, what is the median pitch angle difference between the 2 longest arms, where an arm is defined to be at least this long? So if you go across all galaxies and all arcs, then the pitch angle can differ by as much as 14.5 degrees. 100 pixels is 1 radian. So if you demand that the 2 longest arcs have to be at least 1 radian long, there's still an average of a median 10 degree difference. And even for really long arcs, like 2 radians or 3 radians long, you can still have 5.5 and 2.5 degrees difference between the pitch angles. Right? This is getting to be a really, really long arm, and they still differ by 2.5 degrees on the median. And if we make it the mean, it's even bigger, because there are some galaxies where the difference is huge. So that's why we made the mean, because the means seem to be a little bit skewed. So as far as I know, this is not a well-known result, that individual arms in spiral galaxies can have significantly different pitch angles. Another thing we can do, so the next slide is kind of like the first really interesting data we have. Another thing we can do is look through all our 30,000 galaxies and get pitch angle as a function of radius across a single galaxy. And there have been several papers in the past decade or so that have hypothesized, both for theoretical reasons and from scant observations, that pitch angle seems to differ as a function of radius. We can actually now do a high-resolution plot of pitch angle versus radius as follows. We're going to, remember, so we have the images scaled so that this distance is 100 pixels. So that's the radius is 100 pixels. For each value of the radius, from the center out to more than 100 pixels actually, we're going to ask for every arc, we're going to take the average pitch angle across all arcs independent of galaxy at that radius, right? So for example, at this radius here, at the width of my hand, where going to say that, well, this one, and this one, they all touch that radius. And then we can take an average. And this is what we get. So this is the mean pitch angle is a function of radius in pixels across 30,000 galaxies. There's about 100,000 arcs there or more, 100,000 long arcs. There are different curves because the top curve is across all arcs independent of length. The bottom curve demands that all the arcs, looks only at arcs at least 200 pixels long. And it's like 25, 50, 75, 100, 125, 150, 175, 200. Okay, so all of these curves are just for arcs of longer and longer lengths. Now, it kind of makes sense that the pitch angle goes down as we demand that the arc length is longer, simply because you have to squeeze a spiral arc into a tighter and tighter spiral the longer it is if you're going to squeeze it into a disk of radius 1. Some of this is almost certainly noise. So I told you that our algorithm finds bars. It's actually not all that great at finding bars. In the paper we describe why, and we say we're only about 50%, we only detect about 50% of bars that are there. The reason is because other people have written algorithms to reliably find bars. It's easy. We just didn't focus on it at all. But we kind of do a half-assed attempt to find bars. So this huge spike here at low radius is almost, like I just did this last week. I haven't really looked at it too carefully. But this almost certainly here is just arcs that were mistaken for bars, right? So if you actually have a barred spiral galaxy, our algorithm might try to fit an arc right there. So you're gonna if you try to treat an arm, so if you try to treat a bar as an arm, you get a really high pitch angle. So I think that's what's happening here. At very low radius, this is probably garbage. To the left of about 20 degrees, it's garbage.
So there is something in your algorithm that treats bars separately from arcs?
Yes.
Or they doesn't seem as arcs with a pitch angle?
Our algorithm attempts to find bars that are and then excludes them from the arc fitting. That's way back. So the green thing is a bar. But we're not very good at it because we didn't bother. We didn't bother making it. I mean, we could spend some time making it better, but we concentrated solely on modeling spiral arms. Okay, so I think to the left of my hand is probably garbage. This, I have no idea what this is. I have no idea what the hump is here. And even for very, very long arcs, there's still some structure here, right? If you go out to about 0.6 of a radian, there seems to be a minimum in the pitch angle, average pitch angle across 30,000 galaxies. Then the pitch angle, I mean, this cannot be a bar because these are arcs that are 2 radians long. So it would be, I just can't imagine how you can take a bar, which is basically a pitch angle of 90 degrees, and you can't extend it all the way out to being 2 radians long. So there is definitely something here. The average pitch angle definitely seems to increase towards the center and towards the outside, and there's a minimum, right? And I can see the theorist stirring in the air now. Like, why would that be, right? This is cool. This is cool. I have no idea what this hump is. I have no idea what this minimum is, but there's something interesting there. Here's where the theorists can start cranking up their galaxy simulations and seeing if they can reproduce this. This is noise. So I told you that we scale our images so that the disk is a radius 1. I actually lied a little bit. The images are 256 pixels square. So it's actually 128 pixels from the center of the image to the edge. And it just so happens that puts the disk approximately of radius 1. Occasionally, our algorithm will spuriously find arcs. We'll see the edge of the picture as an arc. And that would be an arc of low pitch angle, because it's almost perpendicular to the line from the center. So this little dip here occurs exactly at 128 pixels. So that's garbage. Down here, though, basically, okay, I'm not sure what's happening out here. This is the part that I'm really, really confident of between my hands. This, I'm not so sure, and that's almost certainly noise. But the fact that even 200 pixel long arcs still have structure leads me to believe that there's probably something something physical happening there. But I'm not sure, right? This is very, very raw data. Questions? So what kind of science can we do with SpArcFiRe, with all the output that we've now described? One thing you can do is we have this huge ARC database. How much time do I have? Am I doing good? Another 7 minutes? We have this huge ARC database now. We've described all the ARCs that we can find in the Sloan survey. So you can go to our database and ask queries. Find, for example, this is a result of the query, find me all galaxies that have exactly one very long arm, and that arm has a very low pitch angle. We don't actually look for rings explicitly, but this query finds ring galaxies. And it finds about 300 ring galaxies. This is just a sample of 9 of them that I chose at random. Some of them are very dim. Some of them have bars. Almost every single one, though, has at least one bright object nearby. And simulations suggest that ring galaxies come from collisions, right? Like a bullseye-type collision. So I'm guessing that these guys are the impactor that went through the center of the spiral galaxy and caused the ring. That's kind of interesting. If you care, we also do star masking, just using source extractors. This is not really original work. It's just sometimes there's a star, a really bright foreground object that distracts the ellipse fit. The very first step of our algorithm is looking for the disk of the galaxy. If you give us an image like this, and if we don't mask out this star, the ellipse fit will try to fit both of these really bright things in and put the center of your galaxy there, and you'll get garbage. So we just use source extractor to extract all the objects in the image, and then we do assume that at the very least the actual galaxy is near the center of the image you gave us. And then source extractor can be used to do more and more aggressive what we call star masking. So before we did this, about 20 to 30% of the galaxies from Sloan were garbage because our algorithm was just trying to fit a bright object into our ellipse at the same time as the galaxy. But now with the star masking, it's almost flawless. So just some observations to sum up. We've run SpArcFiRe on the entire Sloan database. That gives us an ARC database for all ARCs in all galaxies. And you can submit quantitative queries. What I mean by submit is I have a little awk script that I just, I can look through the database. And it takes about 1 second to search the entire database. Although I didn't actually describe it, part of the information we give is a mask for each arm. So we provide the astronomers, the user, with a mask of which pixels belong to which arm. So if you're an observational astronomer and you want to go find out something about this arm, you can use the mask to find all the pixels in that arm and go back to your FITS image and do whatever you want with your FITS image. Okay. The logarithmic spiral arc is often an excellent description of arms, even if the length of the arm is goes around more than once. Such precision will severely constrain theories of spiral formation. I don't know if current simulations of spiral galaxies typically provide logarithmic spiral arcs as the arms. That would be, I don't know if anyone has even tried that, right? If you do galaxy simulations, take an image of your galaxy simulation and put it into SpArcFiRe and see if you get a logarithmic spiral arc. If you don't get a logarithmic spiral arc, your simulation is probably something is wrong. I haven't actually tried that yet, and that would be easy to check. In any case, it definitely enables more detailed quantitative description and measurement of spiral galaxies. I haven't really talked about much science yet, because basically Darren has spent his entire PhD trying to make the algorithm as good as possible. We haven't actually done much astronomy yet. I think the first kind of astronomy we've done is showing that it's hard to define what an arm is and getting pitch angle as a function of radius. That's kind of cool. There's tons of other things we can do. For example, cosmology currently assumes that the standard model of cosmology assumes the universe is non-rotating. We can actually test that by asking, is there an overabundance of ZYs versus SYs spiral galaxies in the universe? And we're actually doing that right now, because some people have already done that and found a bias. We think it's garbage because we think there's some biases in there. So we're about this far away from getting a p-value of the chirality bias in the universe. We can also do vision-based classification of galaxies. We have a preliminary machine learning algorithm. So if you run Darren's code on an elliptical galaxies, it doesn't find any arms, which is good. So now you can actually use the output of our code to discern whether you're actually looking at a spiral galaxy or not. We also, since with this, we now have this huge pitch angle database that nobody else has, we can try to see if we can correlate pitch angle with a laundry list of whatever you want. We haven't done it yet. We've done it with radius, cool. You could do it with color between galaxies. Does the pitch angle of red galaxies tend to be more than blue galaxies? I know spirals are mostly blue, but bear with me. Some people have suggested that even across wave bands in one galaxy, you'll see different pitch angles. We haven't done that yet. We could. The pitch angle might vary with the disk to bulge ratio. It might vary with distance. It might vary with the environment. There's a lot of papers recently that our team seem to be showing that the pitch angle varies with the mass of the central black hole. It might vary with size of the actual physical size of the galaxy in kiloparsecs. It might vary with bar strength. It might vary with arm width, or who knows what else. So actually, the next paper I have on my to-do list is the title is probably going to be correlations of a laundry list of correlations with pitch angle, or lack thereof. And if you're interested, preliminary web interfaces to SpArcFiRe is currently available right here. And we will soon release both the code and the data to the public once Darren is happy, because he's very pedantic and the code is a bit ugly right now. That's it. Thank you.
Well, since we're heading to desserts, why don't we hold questions and just take them upstairs?
Sure.
Or